Effect sizes are often measured in terms of the proportion of variance explained by a variable. In this section, we discuss this way to measure effect size in both ANOVA designs and in correlational studies. Responses of subjects will vary in just about every experiment. Consider, for example, the smiles and leniency case study. A histogram of the dependent variable leniency is shown here. It is clear that the leniency scores vary considerably. There are many reasons why the scores differ. One, of course, is that subjects were assigned to 4 different smile conditions, and the condition they were in may have affected their leniency score. In addition, it is likely that some subjects are generally more lenient than others, thus contributing to the differences among scores. There are many other possible sources of differences in leniency ratings, including, perhaps, that some subjects were in better moods than other subjects, and/or that some subjects reacted more negatively than others to the looks or mannerisms of the stimulus person. You can imagine that there are innumerable other reasons why the scores of the subjects could differ. One way to measure the effect of conditions is to determine the proportion of the variance among subject scores that is attributable to conditions. In this example, the variance of scores is 2.794. The question is how this variance compares with what the variance would have been if every subject had been in the same treatment condition. We estimate this by computing the variance within each of the treatment conditions and taking the mean of these variances. For this example, the mean of the variances is 2.649. Since the variance within the smile conditions is not that much less than the variance ignoring conditions, it is clear that the smile condition is not responsible for a high percentage of the variance. The most convenient way to compute the proportion explained is in terms of the sum of squares conditions and the sum of squares total. For the present data, the sum of squares for smiling condition is 27.544, and the sum of squares total is 377.189. Therefore, the proportion explained by smiling condition is 27.544 divided by 377.189, which equals 0.073. Thus, 0.073, or 7.3% of the variance, is explained by smiling condition. An alternative way to look at the variance explained is as the percent reduction in error. The sum of squares total, 377.189, represents the variation when smiling condition is ignored, and the sum of squares error, 377.189 minus 27.544, which equals 349.654, is the variation left over when smiling condition is accounted for. The difference between 377.189 and 349.654 is 27.535. The reduction in error of 27.535 represents a proportional reduction of 27.535 divided by 377.189, which equals 0.073. The same value is computed in terms of proportion of variance explained. This measure of effect size, whether computed in terms of variance explained or in terms of percent reduction in error, is called eta squared, where eta is the Greek letter eta. Unfortunately, eta squared tends to overestimate the variance explained, and is therefore a biased estimate of the proportion of variance explained. As such, it is not recommended, despite the fact that it is often reported by a leading statistics package. An alternative measure, omega squared, is unbiased and can be computed as shown where k is the number of conditions. For this example, k equals 4 and omega squared equals 0.052. It is important to be aware that both the variability of the population sampled and the specific levels of the independent variable are important determinants of the proportion of variance explained. Consider 2 possible designs of an experiment investigating the effect of alcohol consumption on driving ability. As can be seen, Design 1 has a smaller range of doses and a more diverse population than Design 2. What are the implications for the proportion of variance explained by dose? Variation due to dose would be greater in Design 2 than Design 1, since alcohol is manipulated more strongly than in Design 1. However, the variance in the population should be greater in Design 1, since it includes a more diverse set of drivers. Since with Design 1, the variance due to dose would be smaller and the total variance would be larger, the proportion of variance explained by dose would be much less using design 1 than using design 2. Thus, the proportion of variance explained is not a general characteristic of the independent variable. Instead, it is dependent on the specific levels of the independent variable used in the experiment and the variability of the population sampled. In the section Partitioning the Sums of Squares in the regression chapter, we saw that the sum of squares for y, the criterion variable, can be partitioned into the sum of squares explained and the sum of squares error. The proportion of variance explained in multiple regression is therefore SSQ explained divided by SSQ total. In simple regression, the proportion of variance explained is equal to r squared. In multiple regression, it is equal to multiple r squared. In general, r squared is analogous to eta squared and is a biased estimate of the variance explained. The formula for adjusted r squared is analogous to omega squared and is less biased, although not completely unbiased. In the formula for adjusted r squared, n is the total number of observations, and p is the number of predictor variables.